All right, we're just about ready to start. Let's just sit down. There's a meeting.
It's not even counting yet.
Are you ready?
Just about ready, yeah, go.
All right, welcome to the Secure Hardware Design presentation. My name is Kingpin. To my left is Oblivian. We are from the At Stake Research and Development Group, which was formerly Loft Heavy Industries. Some of our expertise involves portable electronic and microprocessor system design, reverse engineering of hardware-based security products, wireless technologies, and electrical engineering in general. What we want to do today is to understand, as designers, how to properly design and implement security into your product. What we're going to do is, first we need to lay down the foundations of designs involving security to get the process in place, make sure we have solid documentation. After that, we need to understand some of the high-level attack methods that attackers will use to target your product. So we'll run through some high-level attack scenarios. Finally, we'll discuss actual design recommendations and methods of secure hardware design. So these would be actual implementations and recommendations that we've learned over time. What we're going to do is we have a lot of slides, and we're going to try to run through fairly quickly, and those who are interested can come to the overflow session, which I believe is at 12 or 1:30 after lunch. So why secure hardware? This is a question that's becoming very common. It's similar to asking why have a secure network? Well, embedded systems are everywhere now. Internet appliances, any device with networking capabilities, they're being implemented everywhere. In most cases, if you compromise the system, you can access any kind of cryptographic secrets, private data, possibly launch further attacks from that device. So we have routers, switches, crypto accelerators, all of these things that are hardware devices that are now being targeted for attack. Detailed analysis and reverse engineering techniques are available to everybody. There's technical white papers, technical journals that document various attacks on hardware products. Everybody can read these, so as a designer you need to be aware of these and lock down your system properly.
Yeah, and one thing that Bruce alluded to was that secure hardware necessarily won't fix the problems, and what we're trying to present here are ways to alleviate risk out of the hands of application developers and to move the stuff down into a lower level so that application programmers don't necessarily have to twiddle with the algorithms necessarily. And the best security methods are... Break this one up a little bit?
Yeah.
Yeah. Best security methods are when they're undetectable and unavoidable. That way there's less programming mistakes, and application software providers can focus on their task, which is to come up with the next whiz-bang thing, and the security manager on the project, if there even is one, can focus on the lower level hardware, making sure that certain mechanisms are there, and sometimes the security mechanisms can even keep the application programmers in check by having certain bounds on memory and whatnot, and we'll get into that later.
Yeah, so as designers, we're presented with this challenge of making security part of the system and make it our burden as designers, not the burden of the users. Because as Brian mentioned, basically if security features are going to slow productivity or make it difficult to access certain things, people will find a way to circumvent that, including legitimate users. So having security in that point just won't work. So it's best when it's indetectable and unavoidable. And also the means exist. There's a cryptographic system on a chip. There's devices available that are now low cost that you can implement into your system to help make them secure. So as I mentioned, at first, before you even start your design, you need a solid development process. This involves a number of things. You will need to have a design requirements agreed upon. This would be everything from how the device will operate to some of the circuitry you're planning on using. Many times as the product is being developed, a change will be made either to the circuitry or documentation or firmware without re-evaluating the security implications of that change, which could lead to a number of problems down the road if you overlook those changes. So you need to have these design requirements solid, and if there is a change, you need to verify that the security still works.
All right, and then we outline a bunch of, you really should identify the risks of the entire life cycle, not just how to protect certain secrets or, trying to secure a communications management channel. You should really document everything you do, so if, as your product's moving from prototype to prototype, fixes that you implement sometimes break other things, and by having good revision software control, or software revision control, and verbose design documentation, you can sometimes backtrack and figure out, why did this break, and you can take steps to remediate it. The two final things is mainly once you're done with your prototypes, you're moving to manufacturing. A lot of times people just, hand the design off to manufacturing and say produce many times and distribute. You really should look at the personnel. You're basically trusting these people to initialize, especially in the case of cryptographic hardware, where you initialize it and then you ship it out, and hopefully you have a mechanism in there to detect whether it's been tampered with in transit. If you have some type of code signing stuff and somebody replaces the public key in the device itself with something else, then that person has the ability to become the root signer for any applications you download into the device, which would be very bad. You can also, you should then look at end-of-life recommendations. Many times devices will have keys in them. Military is very used to this, and they'll basically shred any type of classified module at the end of use. And as commercial designers, we should really look into that as well.
Yeah, along with that, as far as identifying the risks, there's always this risk management. I know Bruce Schneier talked about this a little bit. As designers, we need to, first of all, define the enemy and know what we're protecting against. This is going to vary depending on how your product is being used. We also need to determine what an acceptable level of security is, and also determine what the cost and benefit trade-off of that security will be. So, we don't want to spend X amount of dollars on a product or on security if the product isn't really worth that. So you just need to identify which risks you have. Identify single points of failure. You need to understand what they are and how do you handle. We talk about this in our system level recommendations a little later on. These points of failure are also not only related to the hardware and software, but they're also related to development personnel, engineers, and your manufacturing process. Actually, there was one other thing on there that I skipped. The third-party design review is extremely important. This will bring a fresh set of eyes on your design. So as you go through your milestones in your product and on a monthly basis or a weekly basis, however often you review your product, having someone else in there as a third party will help you possibly detect design faults and maybe security problems or problems that could lead to security vulnerabilities later on. So, as far as understanding what kinds of attackers will be attacking your product, they vary greatly. As you can see, this slide came from the cryptography research guys. Our recommendations in this talk will basically, we will alleviate the problems of the teenager and the academic columns, but we will also be able to make it difficult for the organized crime and the government columns, the people that have a lot of money and a lot of time and want to break your product. We'll be able to prevent, at least help prevent some of those attacks as well. So there are 4 ways that an attacker can gain access to your product, and this is important to understand in order to know what types of security features you need to implement. The first one is purchase. This would be where an attacker would go to the store, purchase your product, bring it back to their lab, and work on it without any fear of being caught, basically. There'll be physical tamper countermeasures in place that we discuss some of these later that will prevent disclosure of the potential of the system. But if those are bypassed, then you basically would have free reign. The attacker would have free reign. By purchasing the product, you'll be able to determine how the whole product works, but it can be monetarily prohibitive. It might be expensive. An attacker might not spend $20,000 to buy a router to look at it for one security problem. So there's a downside to purchasing. Evaluation is where an attacker would rent the product from a vendor or distributor, often on a monthly basis. This would be to evaluate the product in normal use and also to try to take apart the product. Most of these attacks are treated as a black box. The attacker will be cautious to really tamper with it and open it up because there might be tamper seals and things that would be evident that the device was tampered with, which would probably void warranty, and you'd end up paying a large amount of money to whoever you rented the product from.
Yeah, the other thing about the purchasing and evaluation, a lot of times an attacker will take one of those systems and sacrifice it just to figure out how the internal tamper-proofing mechanisms work. And they can then use those techniques to then go after a system that may be live somewhere. And they'll know how to defeat certain tamper mechanisms, get around it, pull the, it's kind of like a black bag type run into an ISP where you'll pop the lid off, extract the secrets out of the live system, and then seal it back up, hopefully, without leaving any tamper-evident marks behind.
Right, and that goes right with the active and in-service types of attacks, where most of the attacks are possible. The device would be in actual service and in actual operation, but an attacker would still have physical access to it, so if they got into your NOC or into wherever your machines are running. This obviously is a very high-risk scenario because you can get caught red-handed sitting there tampering with someone's router or crypto accelerator, which would be bad. Remote access is the final one. This is where an attacker doesn't even require physical access to your product. So you might not need to have any kind of physical tamper-proofing in place. This would be standard network attacks, attacks through dial-ups and things like that.
Okay, I'm going to quickly walk through a bunch of the different types of attacks that an attacker will walk through. Usually, the attacker will hit the system, hit it with system-level attacks where they don't have very much information in a box. This might just be, after an attacker does a network scan somewhere and they just are trying to figure out what the OS is, and they'll hit it with a port scanner, try to figure out what services it's running. All those types of attacks can be performed remotely. Another type of system attack is before you actually get the screwdriver out and try to pop the lid off, you can see if there's any other, if there's a floppy disk there, you can try to boot off of it. And then if the system's complicated enough, there'll be other file systems that you could mount subsequently and then try to extract applications and data off of it. Okay, so if you don't get anywhere and you're determined to get the box, if you're determined to get the secrets in the box, you probably go out and either purchase it or try to get one under evaluation and get the screwdriver out. If there's tamper bits on it, you have to get the proper bit and start popping it open. Also, if it has a lot of heavily tamper-proofing mechanisms on the system, you may have to use less invasive attacks such as thermal probing or thermal imaging and X-ray. And if there's some vents in it, you could also snake in a fiber optic camera possibly to find micro switches and other types of devices to properly lock down, so when you pop the case off, it doesn't zeroize itself. After you actually get the,
No problem. Yeah, so the circuit level stuff, there's a number of attacks here. Gaining access to the circuitry will let you uncover various design issues and design flaws that you could possibly, or that an attacker would possibly exploit. The attacker could basically create a schematic by looking at the PC board, which is essentially a roadmap of the electrical circuitry. So PC board design and parts placement would be recreating the schematic to learn how the system works. Component substitution, this would be where an attacker would replace a processor with their own firmware, or possibly reprogramming an FPGA to do certain things. Any kind of low-level component substitution to make the device do something that it wasn't intended to do. Active bus and device probing would consist of looking at the various I/O lines, the address and data lines, and other control lines from processors, from coprocessors to possibly determine firmware and how the system operates. The next two, fault induction attacks and timing attacks, have been talked about a lot with a lot of white papers recently. There's some references at the end of this presentation in the notes. These would be determined on a circuit level, but they could be applied to a system level, a non-invasive attack, once the attacker can determine that they can be done. And the final one is an integrated circuit die analysis. This is also a hot topic. This would involve delidding a device, possibly looking at the ROM layout or how the fuses are burned on the ROM or possibly in an FPGA. So firmware attacks are the lowest level of attacks. Firmware, as most of you know, contain the program code that would control the embedded system. Analyzing the firmware obviously gives you a low-level understanding of the product, and it will also allow an attacker to make software changes, possibly to bypass failure detection by removing fault checks or maybe authentication measures. So along with having the circuit, schematic, and the firmware together, you basically have you can understand how the entire system works.
And then there's one more. There's one more attack that kind of fits under the system level, and that is a lot of vendors out there, like printers specifically, and a lot of PC makers have their BIOS images right up on their websites. So you can just go out and download strings for embedded backdoor passwords, or just there's a lot of decompilers out there now that will definitely give you the generic flow of the system, and it'll hints on where you could possibly tweak it, and then perhaps download into target systems to bypass those types of mechanisms that KP just mentioned. What needs to be protected? Well, basically everything we just talked about that can be attacked. Most specifically are the firmware binaries. Many times it's a very low-cost attack where you can just go out and view the stuff that's sitting out on open websites, usually sport websites. Next is the boot sequence. You definitely don't want to have the ability for applications code to step back and reprogram firmware. That's a bad thing. Cryptographic functionality, if it's in the device, which should be, you don't want people messing around with those and weakening the algorithms. Sometimes the algorithms can be weakened and remain undetectable. Or you can have them leak out secrets. And the configuration and management channels need to be protected, because if you don't protect the management channels, then the device can always be configured in an unsecure manner. So now we're going to talk about some of the countermeasures to the attacks we just discussed. First thing I'd like to stress is the need for a trusted base, which really comes from the old DoD trusted systems evaluation criteria, which is now morphed into ITsec common criteria. Example of a trusted base is a lot of people are calling them security processors. I like to refer to them as a cryptographic system on a chip. In the old days, in the 60s, 70s, a lot of people were embedding security reinforcement hardware as a module, and these things cost like 10, 20, 30 grand at times. And through the advances in technology of squeezing more and more devices onto one chip, you get basically the same functionality in a $20 or $40 part that you can embed onto a router, firewall, or any other type of specific NIC, or drop it right on the motherboard. With this, you don't need an expensive tamper envelope around the entire box. You have it somewhat restricted to the die itself, and that really does take the attacks out of the hands of most attackers. But as you can see from Marcus Kuhn's paper on the state of smart card security, he successfully, using fuming nitric acid and stuff, removed all the protective epoxy and could actually do a die analysis attack. But I would have to say that that is a tamper-evident attack. The firmware can also be protected inside the trusted base, and you also have mechanisms that can verify the integrity of of software that isn't necessarily inside of the trusted base. So some examples of the single IC devices are the IRE SafeNet DSP chip, the PCC ISIS, and the security coprocessors. There's the, which I really like, the IBM 4758. These guys did an excellent job, and they really know the field well. And Chrysalis ITS just came out with the Luna 340, and I haven't gotten any information on that yet, but I'm trying to get some documentation from them. One of the things that runs inside of the trusted base is a security kernel. And what that kernel does is it enforces the security policy for the system, and it also has the ability to decouple the keys from any OS calls or application level calls. Instead of having the application software generate the key itself, you can just ask the security kernel to go perform an encryption operation without ever knowing what the key is. Just say use key and register 1 or A or B, and then encrypt it and just give me the result. I don't need to know the actual contents of the key, I just need to know whose key it is. A good example of this is cryptlib, and it's written by Peter Gutman out in the University of Auckland. I recommend it. Unfortunately, I don't have any way to really, without poking Joe in the eye, walk through this diagram, but I'd be glad to walk through it in the extended deeper knowledge session. But basically, the CSOC there will hold the microprocessor in reset until it can verify its firmware. And once it's verified, it'll let the microprocessor out of reset and then to boot off of its firmware. It also shows by that memory mapped bus to it'll control the communications interface. There'll be 2 buffers, an encrypt and decrypt buffer, and the CSOC will be told to do an operation on one buffer and then tell the NIC interface to pull it out of the other buffer, but I can go into that in greater detail in the other room. Failure modes. Determining, one of the things that a proper design practice calls for is a security fault analysis. And what that is a set of procedures and tests that you perform on your product to determine how it responds or reacts due to certain environmental or induced attacks, such as excessive heat, cold, if a chip fails, if memory fails. Will your system fail open, fail closed? Will it fail in a way that the ciphertext is mangled somewhat? There were some papers released about vulnerabilities and key leaking through Chinese remainder theorems based on hardware failures. You really need to determine what the response merits depending on the failure detected. It may require that the system's halted and to send some type of message to the crypto officer or whoever manages the device to come, fix me. You may want to set a flag and continue if it's not a catastrophic failure. Or if you set up your detection circuitry properly, you can possibly determine an attack over time. And if the temperature drops too fast, that may be an indication of a tamper event, and you may want to zeroize certain secrets out of memory. Okay, management interfaces, as I mentioned before, if you don't secure these things, what good is the rest of it, really? Don't include service backdoors. I did some work on a SSL accelerator, and lo and behold, they had backdoors embedded in it, and they also had a web-based management interface, and that web-based management interface was not protected, even though the device was used for accelerating SSL traffic.
All right, so now we have some firmware recommendations, which is basically designing some of the low-level boot code, system initialization issues, and also dealing with writing firmware in general.
Here?
Yeah. All right, secure programming practice. This is basically just using common sense guidelines when you're writing your software. This would consist of removing symbols, debug symbols from your code, using compiler optimizations, which might help. It will, not only speed up the code possibly, but also use some of its internal macros and things to help obfuscate the code. It might make it a little harder to reverse engineer. One thing that we've seen is to have 2 or 3 versions of the firmware. This would have a development version, so the version of the firmware as you're developing your product, possibly an engineering version that might have less of the debug information kind of moving towards a production, and then the production version, which won't have any of these symbols, no debug information, things that aren't needed in the actual product. We've seen a lot of companies that will ship their firmware with all of this information internal to it, and as you're reverse engineering the device, or you disassemble the code, you end up with a lot of useful information. Also, as far as removing the debug information, it's kind of hard to see, but on a lot of development environments and compilers, there's a button. All you do is click on that button. So just do it. It's easy. It will remove a bunch of opportunities to attackers. Next slide. Buffer overflows, Bruce Schneier just talked about a little bit. They're highly publicized, attempted often, and they're also attempted on hardware products, not only software, as you've seen a lot of problems with Microsoft in particular. This also highlights the point of having source code reviews. I'd mentioned having third-party design reviews for the entire product, but also having people look over your code, make sure you don't have buffer overflows in there, make sure you don't have any blatant problems. This helps a lot, especially if you're staring at your code for 15 hours a day for 3 weeks or something. You start to miss a lot of things. So having a fresh set of eyes is important.
And one thing about third-party reviews, a lot of people who are designing secure hardware, specifically cryptographic modules, will generally think that what the heck's it called? I can't believe it. FIPS 140-1, I think. It's got 4 different levels of certification. A lot of people think that's a third-party review. It's really not. They come in before you sell the. You're trying to get your device certified basically to operate at a certain security level, and a lot of times people mistake that as a third-party review. They'll just look at your product after it's already gone through all its design cycles, and just give you a pass or fail, and sometimes they'll give you some comments on it, but generally I don't think it's too helpful. The next slide here is about the boot sequence. Unfortunately, this doesn't even look good on the slides that were printed out, so it's going to be kind of hard to go through. But the top part is a normal systems boot sequence, and the bottom one here is got the trusted base module, the cryptographic system on a chip, and that dashed line shows the normal boot and verify type steps that a system will perform when booting. Usually what it'll do is it'll verify the boot ROM firmware itself inside of the CSOC, and then if that's okay, it'll proceed to the next thing, and it'll first go out and verify like firmware stored on an off-chip device. If that's okay, it'll go out and start verifying kernels, applications, and whatnot. But you can always like roll back your train of trust back to that back to the code that's inside the CSOC that can't be necessarily tampered with. Runtime diagnostics. Let me just run through this. It's really good to perform periodic low-level checks on the hardware. The best example of this is whenever you do a key generation routine, you should really make sure that the numbers you're getting are random from the random bit generator. If you're getting all ones or all zeros due to some other attack, that's a bad thing, or the device may have just failed. You can normally do, I think for FIPS there's like 3 or 4 tests you're supposed to perform before accepting a random number to generate a key with.
So yeah, as far as these runtime diagnostics are these periodic low-level checks. They can be done with the key generation, but it's also just to perform checksums on memory, make sure the firmware, the ROM, and the RAM is consistent and no data has been changed. You get what you expect. A lot of this could be done in hardware, but you can also do some of this in firmware, which is why we mention it in this section.
All right, secret management, it's pretty much a no-brainer. Never leak unencrypted secrets out. A lot of business applications require the escrowing of keys for like large backups and stuff. You don't want to, if your module is tampered with or just, it burns in the building, you don't want to lose vast stores and stores of unencrypted data. But you really need to know that escrow mechanisms are a security risk, and if required, the key generation and escrow should be done in the presence of humans. Once you get the key encryption key out, you should really do your best at protecting that thing. And if you escrow one key encryption key, then all the other ones can be encrypted with that key, and you only need to protect that one key in a safe, in the bottom of a salt mine with armed guards. Cryptographic functions. Again, I tried to stress the importance of having your functions, not being able to have them twiddled with. And a lot of people have been moving them into accelerator chips, which are ASICs. Usually they're difficult to modify. That's good if you're an attacker. That's not good if you're an attacker, and it's also not good if you're a developer, because if the standards change, SDR right now, moving away from DES into AES, there's going to be a lot of obsolete hardware devices out there. What you're seeing a lot now is a lot of CSOC and FPGA-based cryptographic implementations of algorithms. And what that allows you to do is to update the devices as needed. It also enables certain companies to skirt around export controls. Field programmability. This is touching upon the firmware being distributed on support websites. It would be nice if you could encrypt it, but if somebody goes out and purchases the device, they're obviously going to be able to extract it with a standard PROM programmer or reader of some sort. Still weighing the benefits of encrypting it over just code signing. If you sign your code and you have your public key or verify key embedded in the CSOC, you'll at least be able to verify its integrity. So if somebody else changes your firmware in some way, they won't be able to run it on your processor because it'll fail the check.
All right. Circuit layout and design issues we touched a little bit upon on some of the attacks. So here are some recommendations to make your device secure. Test points. Basically, when you're doing your PC board design, actually, before I even go through these, proper PC board design is really an art form. You should probably either outsource or work closely with a full-time board designer if there's one in your company. They know the CAD software, they know the tricks of the trade, they know a lot of the physical PC board issues, which could help keep your product designed properly from a board level. So you want to remove unnecessary test points. A lot of times, if you have too many test points, they'll allow unwanted noise and interference to pass through the board. You'll see in these next few slides, I'm going to talk a lot about keeping the EMI and the noise interference down. We'll explain why in a few slides. So you want to keep your traces as short as possible for that same reason as far as noise, but it also might make it difficult for an attacker to access those lines. You can also route the signal traces on internal layers of a multi-plane board, which is good for production but not good for development, because then the engineers won't be able to access those lines. Also with vias, you can have buried vias, which would also be in the inner planes of the board, which again is good for the production but not good for development. Keeping the ground plane separate is also helps with noise issues, and if you alternate the power and ground planes as you go through your layers, it helps add a little level of tamper detection if an attacker was trying to drill through your board to access some of the lines in the multi layers. They might drill through power and ground and possibly short those together. Parts placement goes hand in hand with PC board design. You want to make sure that all of your critical components, all of your memory devices, possibly cryptographic processors, are difficult to access. So if you had possibly two boards in your design, you could place all of your critical components in between the two boards and have maybe a tamper response or a tamper sense line somewhere in the connector. So if those two boards were taken apart, you could zeroize memory or do some kind of tamper response. An example of the parts placement I will actually touch on a little bit later too is there's two advisories that I recently released on USB hardware tokens, which if you're not familiar with them, they're basically little embedded systems that will store private data used for authentication and public key applications and things like that. I looked at two devices, and both of those devices they used an external serial EEPROM, which are extremely common in the engineering industry. They're also extremely easy to read data out of. And the reason these attacks were so easy is because these parts were placed, they were easily accessible on the PC board. So as I opened up the product, I could easily clamp on to the EEPROM devices. I didn't have to deal with any kind of tampering or obfuscated placement of the parts. So also proper power filtering and the noisy circuitry, that's also part of noise. The reason you want to reduce the noise issues is because there are some attacks, such as Tempest, which we'll touch on also later, that make use of the stray noise generated by the device. You could possibly recreate images from a monitor or gain secrets or private data. So you want to keep the noise down also for FCC regulations, and if you're doing medical devices, FDA regulations, you need to keep the noise down. And that's just a good design practice. So physical access to components, I just mentioned the USB devices. If you look up on the screen, I know in the printout this is really hard to see, but this is one of the USB hardware tokens we looked at. What you can use is epoxy encapsulation to coat the critical parts to make them harder to access. Unfortunately, if you don't implement that right, the coating does nothing. On the device on my right, there's a Cypress microprocessor, which contains the firmware for this USB device. That was properly coated in epoxy. However, you could scrape that off or possibly use some kind of chemicals to remove that material. But on the other side, there's a serial EEPROM that's covered in epoxy. But then there's those 8 silver pads, which is an expansion memory footprint that isn't protected. The nature of the serial EEPROMs will allow me to attach probes to the 8 unprotected pads and read all of the memory of that protected device. So there's epoxy coating on there to prevent me from touching that device, but I can still read all of the data in it. And that led to compromise of the device and also led to a security advisory. So power supply and clock protection, this is basically you want to take precautions to prevent intentional variation of power and clock, which a lot of attacks are based upon. You want to set an operating envelope by having minimum and maximum limits of your VCC rail of what your clock should be. If there's any skew, you should be aware of that. To protect against voltage variation, you can use a number of watchdog circuitry ICs that are available from a number of companies, and also standard DC to DC converters, regulators, things to keep your voltages in line. You can also monitor clock signals to detect variations. You could feed them back into your processor and have that as a check. So I/O port properties, this will be what do you do with all of your unused I/O pins on your processor or your FPGA. You need to either disable all of the ones you're not using, which will prevent noise. For example, on a Motorola 68000, there's a pin called clock out. And what this is just used for testing of the internal 16 megahertz PLL, but that defaults as on. So if you don't turn those unused pins off, that thing's going to just send out 16 megahertz signal on the board, and that's going to generate noise, and that can lead to a lot of issues. What you could do is, especially in FPGAs, you could set some of your unused pins to detect probing, which is what we call a digital honeypot. What you do is set the pins as inputs, and if you detect a level change, possibly if someone pulls a pin to ground, the FPGA will know that, and you can assume the device is being probed, and the circuitry can handle that properly. And that's a low-cost method that can be implemented. So when you're dealing with your programmable logic and memory, you want to make use of all of your on-chip security features. There's security fuses and software protection bits and software protection strings that you can send to the device and make sure that it won't leak the data. It will disallow somebody from reading the contents of the memory. Although there's sometimes ways to bypass that fuse, for example, deleting and viewing the die, which I mentioned earlier, which is popular in smart card attacks and mentioned in one of Marcus Kuhn's paper that I believe is a reference. You still need to take steps to protect the firmware as well as you can. FPGA design, make sure you cover all of your conditions. You don't want to get into some undetermined state and basically get your system thrown off into oblivion and not be able to recover from that.
And another thing that's nice on more complex systems is to have an advanced memory management unit. And what this will do is it'll sit and it'll monitor the address and data lines, and also like the, at least on the 68340 series Motorola processors, there's a 4 bits that determine if it's like, if the system is running in supervisor, user, or if it's a DMA operation. And a lot of times it's nice to monitor those addresses and fetches in the different states, because you can, you can keep the programmers in check to make sure they're not writing bad code and like using DMA to copy stuff out of your tamper non-volatile storage memory out to the SCSI port or to a network port. You can also use it to protect firmware so that if you're in a certain mode, you can't update firmware on the board if it's in flash of some sort. Other things you can do is if somebody's attacking a system, a lot of times what they'll do is they'll stick a firmware image in there and just start probing different memory locations and start jetting them out any types of communications port. And you can set trip points in the address space. So if somebody tries to do a read out of a space that doesn't have a device on it, it'll stop it right there. Some processors will actually, once it gets to the end of a defined memory range, it'll wrap around to the beginning. And by using this memory management unit, you could blow into a FPGA or even a PAL. You can trigger those types of attacks or probings. ComSec requirements kind of touches upon making sure that encrypted stuff stays encrypted, and if you're going to send red information, which is usually determined as classified information in government circles, you want to blacken it before it goes out of the box. And also, a lot of times people will share buses on systems, and just make sure you're turning things on and off properly. And you don't want red data on a bus when it's being accessed by some type of black routine. The enclosures, we're basically going to talk about some tamper-proofing mechanisms here. Don't go into great depth because this could be an entire talk all by itself. There's really 4 different classes of tamper-proofing, and when I say tamper-proofing, it doesn't mean that you cannot tamper with it. It's just a classification of anti-physical type attacks. Usually there's resistance, evidence, detection, and response. The first 3 are actually the first 2 are actual mechanisms, and the 2 final ones, detection and response, are more of a systematic handling of what the first 2 perform. They're most effective when layered. So if you have like a seal, and then there's hardened steel case with maybe a medical lock, and then inside of that you have micro switches, and you can wrap the entire thing in epoxy. That's effective layering. It just makes the attacker's job a lot harder. Some examples of tamper resistance is hardened steel cases, locks, encapsulation, or some types of potting over material, security screws like you see on the bottoms of set-top boxes, tight airflow channels. There's a certain angle of incidence that when you're sending a fiber optic cable in, it'll bend far enough so that you can't get enough light back out to feed into a CCD camera. The side effect of all tamper resistance is tamper evidence. Usually if someone takes the Sawzall to the hardened steel case, you can go look at it and notice that someone's been cutting through your equipment. tamper evidence is basically a major deterrent for minimal risk takers, and that can really help if you've got some type of equipment evaluation program, and you want people to go out and evaluate your equipment. It's a good way to get the stuff in and people feel more comfortable with it, but it also opens up a very lucrative avenue of attack for many minimal risk takers. And simple seals and tapes, maybe a special enclosure finish or micro switches can help deter people from just popping it open, at least without not you knowing it. I mean, you have to send the device back to them, so they're going to inspect it. Actually, not everyone inspects it, and that's another problem. Tamper evidence, this is basically temperature sensors, any types of radiation detection, magnetic switches of sorts. Nichrome wire is a device that is sometimes used to wrap a device before it's potted, and the physical properties of nichrome wire are when you cut the wire, it changes the resistance and you can detect a voltage drop. Nichrome wire is also susceptible to temperature variations. A flex circuit is like a serpentined pattern on usually like a flimsy plastic coating, and you can sometimes wrap those around I/O ports specifically, or I've seen people even wrap them around boards, but the milling process of flex circuitry is not too fine, so you can usually sometimes drill holes in without hitting or breaking the serpentine flex. Another thing is they're very difficult to work with in manufacturing when you're bending them and folding them around I/O ports. A lot of times they break, and it can be a pain. Tamper-proofing is not easy, and it is costly, and that's why I'm trying to stress the use of these more inexpensive cryptographic systems on a chip, because you don't necessarily need to worry about most of this stuff in those cases. But if you do apply these techniques on top of using a cryptographic system on a chip, it definitely makes the attacker's job a lot harder. Tamper response, this is the end result of any type of detector that you have in the system. Generally, the result of tamper being detected is to go out to a device and erase the maybe key contents or any type of logging, audit logging you may have collected. Many times a tamper response circuitry requires a battery, so the system can have an active tamper envelope even while the system's powered down, and that is very difficult for engineers to design, especially when you're using ion and radiation detectors. Those tend to be relatively costly, and they can be very difficult to implement. Sometimes you'll want it, sometimes you might detect tamper, but it may not warrant a zeroization. You may want to audit the information. It's another result, a resultant of.
A good example of some of this tamper response, actually, I guess I should say it's a bad example. We were investigating a time-based hardware token a few years ago. This device did have some tamper responsiveness that was supposed to zeroize certain data if you removed the cover. What we did is we had one device that was basically the sacrificial lamb. We removed the cover to see where all the components were laid out. And on a good card, a good still working card, we cut away only the piece that we needed. And that wasn't detected by this tamper response system, so we could probe the parts that we needed without having any of those content zeroized. So it's another example of you need to implement this stuff correctly in order for it to serve its purpose. So RF emissions immunity, this is stuff I kind of touched upon a little earlier. EMI shielding is important. This can be in a form of coatings, sprays, any kind of housings. What you want to do is you want to reduce EMI in your system, mainly because of tempest monitoring, which is basically recreating EMI for monitors or keyboards, recreating the signal on an external monitor, external device of some kind. And basically the simple explanation of this is that as voltages are applied to the CRT of the monitor, there are spikes and high voltages that generate this noise, and it creates detectable spikes that could be recreated. There are protection methods available for this. there's soft tempest fonts, which is something that Marcus Kuhn developed, that will smooth those spikes by using grayscales and colors, which is an interesting approach. Also, you want to be aware of ESD protection. An attacker might possibly try to break or destroy your system or make it do something it wasn't intended to do by injecting it with high voltage signals. Protection from this, you could just use TVS devices or diodes, which are easily available. External interfaces, you want to be aware of devices that have access to the outside world, which would be basically everything. Anything using serial ports, phone lines, possibly compact flash. Brian touched on this with his Intel net structure problem, which basically had this serial port that would give back the MAC address of the device, and by using that MAC address you could determine the administrator password of the box. So you need to be aware of what data is being sent out of those ports, possibly encrypted if you can, that would be good. Also be aware if any of your external interfaces provide access to the internal bus. That can give a lot of headway for the attacker. An example of this is, Brian will actually give you an example.
Yeah. One example is like token interfaces. A lot of times you'll have like an I button or some type of data key like in a STU phone that'll have access to the internal buses, and many times you should obviously gate those buses properly with the transceiver. I don't know if too many people know, but a lot of times, even through transceivers, there's leakage, and if you drop a couple low ohmage resistors in line with those data lines or even address lines, you can prevent leaking. It's not really a covert channel, but you can prevent bus leakage that way.
Another example of a real-world case of this is the handspring PDA, which is a Palm OS device, kind of like the Palm Pilot. They have this springboard module, which is this expansion port that you can design little hardware expansions, kind of like cartridges for. That whole springboard module connects directly to the Dragon Ball 68328 processor in the device. Because it's a handheld device and it's kind of like a consumer device, there might not be any security problems there, but if you wanted to use some kind of expansion module in your device, you want to at least be aware of what you're giving people access to. Also, you disable all of your diagnostic functionality, your JTAG, things that would possibly help an attacker probe the device, gain data out of. One attack as far as token interfaces that we had looked at was with the USB keys again. We wanted to monitor which commands are being sent to the USB key and how the USB protocol, what data was being sent back and forth. By doing that, we could possibly generate incorrectly formed USB packets, see how the device responds. So if we can monitor that traffic stream, which wasn't encrypted or anything because it was using the standard USB protocol, we could analyze that a little deeper. So, in conclusion, there's a lot of data here, I know, and if you have questions, you can either come up now or we can break out in that other session. But as a designer, you want to think as an attacker would. Now, this isn't just keeping up to date with all of the attack methodologies and things which we mentioned at the bottom. This is reading this information and seeing how various attacks are done. That way you could possibly think, okay, well, if somebody is accessing the serial EEPROM in this USB token, maybe I should protect these devices in my product because someone might attack it. So you can prevent these attacks before they happen, which is a strategic approach, and it's something that by designing security into your product from the beginning will hopefully help. You want to allocate time to break your product. This goes along with the design reviews. Try to catch problems as they happen instead of looking at them all at the end and having to go back and redesign. So peer review, third-party analysis. No. So the next two slides are references and additional reading. Hopefully they'll show up in your notes. If not, we'll have we'll put this up on our website, probably at stake.com, maybe in a week or two. So if any folks have questions, feel free to ask. I don't know if we have a microphone anywhere, or you can just yell really loud, and I'll repeat the question. No? Oh, there's, all right, there's a few.
Is there a mic? Oh, power differential analysis attack.
Actually, would you mind coming up here and using the mic? Sorry, that was a long question. It had to do with differential power analysis, so. Oops.
Thank you. Basically, what I was asking was if you knew of a good circuit design to prevent differential power analysis. I haven't come up with a way. I've been thinking about that in circuits that I've designed, and I haven't come up with a way to equalize power consumption short of putting something that consumes a whole lot of power in line with the circuit, which is not desirable in small devices. Do you all know of a protection against that?
Offhand, I don't. I know there have been some papers written about that, but I don't know if it's from a circuitry point of view. It might be from thwarting those attacks in some software way. But yeah, that's definitely that's a topic that needs to be addressed, and hopefully,
All right.
between some of us, we'll be able to come up with something.
Cool. Thank you.
Thanks. Any other questions? No? Okay. Well, thanks a lot. Hopefully you guys learned something. And bye. Amper detection and stuff. So what you could do with the clock, actually I'll use this example again. The area that we cut out of this time-based token was to access the crystal, which is a 32K, just standard clock crystal. By changing the clock signal, by speeding it up, we could view more iterations of this particular device, which would give us, I'm trying to be a little covert about it, but I think people know what it is. Every 60 seconds we got a new number. So what we were doing is by speeding up the clock, we'd get more numbers, which we could then look for repeated sequences, possibly to see if we can determine the secret based on the numbers that we get. And then by slowing it down, we could single step, make it easier to do external measurements with like logic analyzers and all those tools. But definitely for like time-based things, speeding up the system is going to lead to some interesting things.
And one other thing you can do is in many more complex systems, there's actually different clocks in the system. And if you could slow one down before and leave another one running at the proper time, you can throw things in out of sequence, especially like bus transactions and stuff.
What about countermeasures?
Well, basically, I'm using like some type of PLL and some type of feedback loop to make sure that the thing isn't, being driven out of skew, or if you have a temperature sensor, if they're trying to cool down the crystal so it operates at a slower rate.
You could also use, I think Maxim makes some kind of watchdog things that need to be either set or reset at a certain time. And that time, well, you could probably use one of those to thwart that. But if your whole system is running off one clock and they're changing that one clock, it makes it difficult to do.
Earlier in your presentation, you were talking about some hardware device you were really enamored of. What aspects of it caused you to step back and say, yeah, these guys knew what the heck they were doing? But what about the design you really appreciated?
It was specifically the, I hate IBM part number schemes. It's the
3470.
No, the 40. Hold on. I want to get it right because
4758.
Yeah, and it's their PCI secure coprocessor that they had developed. It came out of Watson Labs in upstate New York. What's his name? Steve Weingart. He's been in the building secure coprocessors for a long time. He worked on the Citadel project, and that was the one that they actually used the nichrome wire to protect the actual mechanism, and then they dipped that in epoxy. And he's been around for a long time, and he really looked at it. But he approached the problem of protecting the secure coprocessor by layering the tamper methods. They used epoxy, they used this nichrome weave. They actually had one weave around it, and then they wove it a different way. And they actually had, I think they had 3 different layers of weave. So if you tried to go in at it at any different angle, you would probably sever something and get busted. They also, it was a, it would zeroize certain things out. What else did they do right? Just the whole way they set up their manufacturing processes, and they initialized the card at the factory, so if it went in transit, they would be able to detect tamper at the other end. By doing a secret check inside the box. So if it had been zeroized, you wouldn't have been able to perform that check. What else? They also had the radiation detectors, which I thought was pretty phenomenal. One thing that was pretty interesting was they had I'm still kind of torn on it, but the way they had the battery, because any type of high current sensor is going to require a battery replacement quite often. A lot of people embed the batteries inside the box, so in order to replace the battery, you have to open the box, tamper it, replace the battery, then reinitialize it and send it back to the customer. With IBM, you had a window where you could pop the battery out, stick it back in, close it, and continue operation. What else? The one downside to the IBM processor was the fact that it was a PCI card, and the PCI card had to go inside of a larger system enclosure, unless you had not a rugged, but an ongoing inspection policy where you have to go and look at the thing to see if it's been physically tampered with. Somebody could tamper with this thing, stick it back in the system, and you wouldn't know if somebody had messed with it because you couldn't see the evidence of it because it was enclosed in this larger enclosure. I think they were the first company to achieve FIPS 140-1 level 4 because they had the temperature stuff in it, but it lost its 4 when you stuck it into the system, and it only became a 3. Any other questions? We could just talk to policies or.
What are your thoughts on the Dow Semiconductor?
I like the iButton actually, but he's done a lot more research on it.
Yeah, I actually designed the iButton into a medical product that I worked on a few years ago to do medical or to keep tracks of the medicines and things like that. There are a lot of different types of iButtons. For those who are wondering, go to www.ibutton.com. There's a lot of different types. We do have the Java Ring cryptographic button. We have some of those. We haven't looked at them too much yet. We are building up our lab, so we'll be able to, and we'll have some space to work on them. But from what we can tell, they look pretty good. They do have some at least their literature says they have some tamper response systems. So if you try to open up the button in some way, it will zeroize the critical memory, and I guess kill any kind of crypto keys that are in there.
The thing I like about it is keys are generated on it, and the secret components never leak out. And I just think that's the proper design for any token-based authentication mechanism.
Actually, shameless plug for those who want more information on the iButton. If you go to right. We don't get paid for this. Go to where is it? I think it's there's the white paper that I wrote that kind of describes some of the attacks that could be launched against it, and also kind of goes into a little higher level review. Just go to loft.com, l0pht.com /Kingpin, and then go to the analytical section. There's some white papers there, so that has some other information on it. But yeah, we're definitely going to be looking at them more, and they've caught on a lot in European countries. The U.S. Postal Service uses them here to keep track of their postal people as they go from box to box, but it hasn't really caught on too much yet, and I think it will. Any more?
I think that's great in a military application. I don't know how much, if you're in a multi-level office building and you knock off the thermite charge on the second floor, I'm sure the fire marshal in town wouldn't think too. But you could use tactical amounts of setting off certain things, but I honestly don't know if there's some statute in commercial law governing products. After having that done to it, no, it's physical destruction of the medium, and unless you're an alchemist or something, and you can transmute the melted platter back into a non-melted platter, I don't think you're really going to pull anything off of it. Right. Well, I mean, if you did it right and you did it in like a ring pattern or something, so it just drops right down on top of it. With the Unix box, there's more of a chance of recovering a super block of some sort, but if you blow away the inner track on a standard IBM IDE or something, you're going to take out block 0, hose your fat table. Has anybody ever seen thermite used in a commercial device?
No.
I know the Navy used them on some sub file cabinets at some point, but that's about it that I know of. In commercial environments or military? Oh, really? Cool. Banking, financial, or maybe even in the city somewhere?
No comment. Cool.
Is that under the table, or is that like just a legitimate product, or is this someone's like homebrew idea of tamper response? Oh, interesting. Are you at liberty to discuss that product? I'm just interested. I'd be fascinated to read up on that. Oh, okay. In the works, I take it? Oh, cool. That's funny.
I don't think that's
Any other questions?
You would touch briefly on bad attacks.
I'm sorry.
Can you guys break down the kinds of attacks?
Yeah.
You have particular method of shielding that you prefer overall?
Not really any particular method. There's a funny picture that for the medical device that I designed, we used an EMI spray, which is just a metallic type of spray that was on the inside of the device, which worked pretty well to keep the noise down. It actually worked extremely well, and it helped us pass the FDA requirements. I forget what the dB drop was. If you were really interested in the details of the spray, I could probably dig out some of the test results. But it was really useful, and I think it was pretty cheap as far as compared to actual metal housings and things like that. But there's a funny picture in here. Yeah. Can you see that picture, or is it pretty dark? That's a completely Tempest-proof PC that actually Dark Tangent took this picture a few years ago. I think he was trying to sell these. But this type of thing obviously isn't going to work for a portable product unless you're Grid or something. But yeah, I do prefer sprays, and it's also because they can put them on at the manufacturing house of whoever's making the housing, so it's really easy. You don't really need to solder on any kind of RF shielding and stuff. So that's what I'd at least try at first. Anything else?
You have a question there?
So any part of the talk that we either went over too fast or you wanted to know more about? Now that there's a huge screen and we can point to stuff?
Yeah. What about?
Do you know key generation for devices like
I don't know. I want to say the Rainbow iKey 2000, the USB hardware token. Just from glancing at some of their material, I think they generate it on their key. I can't say if they do it right, but I think they do.
I know the BBN Safekeeper does a pretty good job at key generation. They use a hardware, I think it's the Tundra random bit generator on there. And then they also perform a bunch of tests. I mean, anybody who conforms to the FIPS guidelines for, I know 3, I'm not sure if 2 conforms to it, but they have a series of tests that have to be run before the random bit stream can be used as a key. Any other questions on, are there anybody here from hardware vendors? No? Seems interesting. Except for you.
Government contractor, maybe.
All right, well, thanks for stopping in then.
Thanks.